Okay, welcome back to part two. Hopefully you guys have a nice little break and are ready to continue with chemical equilibria. Okay, um, so now I want to go, not really go back, but I want to go into more detail on how K and the reaction equations relate to each other. Okay. Okay. How do K and the reaction equations relate to each other? For example, what happens when we reverse the equation? Okay. When the reaction equation is reversed, K is inverted. Okay. And this looks like a C invert K. This makes sense if you think about it. So if we have some reaction A, B goes to C, okay, the K for, we'll just call this F, is equal to products, C, over reactants, A, B. Okay. Now if we reverse the reaction, now we have C goes to A plus B. So the reverse equilibrium constant must just be this inverted. Okay, because now the products are A and B over C. Okay, so K is just inverted for the reverse when a reaction equation is reversed. Okay. Number two, what happens when you multiply coefficients in the equation by some factor? Okay. So multiply reaction equation by some factor. When you multiply the reaction equation by some factor, you raise the equilibrium constant to that same factor. Okay, you raise it to the power of that factor. Okay, for example, if we have A plus 2B goes to 3C, our equilibrium constant is C cubed divided by A times B squared. Okay, that's our equilibrium constant. Now, if I multiply through the whole equation by some factor n, doesn't matter what it is, then I have n moles of A plus n times 2 moles of B goes to n times 3 moles of C. Okay. We rewrite K in this case as equal to the exact same K as before, so that would be C raised to the third value divided by A times B squared, that would be 2 squared, and then we take the whole thing and we raise it to the power of the factor that's been multiplied through. Okay, in this case n. Okay, straightforward, fair enough. Next, what happens if you add two or more chemical equations to obtain a new overall equation? Okay, so what happens when you add two or more equations to obtain an overall equation? Okay, in this case, you multiply the corresponding equilibrium to constants together. you multiply the equilibrium constants together. For example, if I have the reaction of A decomposing into 2B, I have a rate equilibrium constant equal to B squared over A. Okay, and to this I want to add 2B goes to 3C. So I have a K, let's call this 1, and K2. Ends up being C raised to the power of 3 divided by B squared. If I add these together, say that these are two elementary steps in a chemical mechanism or a reaction mechanism, and I want to add them together to obtain the overall reaction. In this case, 2B cancels out, and I end up with A goes to 3C. That's the overall reaction. Now the equilibrium constant for this reaction is simply K1 multiplied by K2. So we end up with B squared divided by A multiplied by C cubed divided by B squared. B squareds cancel out, and we end up with C cubed over A, which is exactly what we would expect if we were to just look at this reaction and form the equilibrium constant based solely on that reaction itself. Okay, so it makes sense. It makes sense with what we've already defined as the equilibrium constant and how to express it. Okay, let's look at an example for this. Say we have some reaction between nitrogen gas and hydrogen gas to form ammonia gas. Okay. Equilibrium constant here is equal to 5.6 times 10 to the 5 at 25 degrees C. Okay. This is a value that is determined experimentally. So I would just look this up in a book somewhere if I needed the equilibrium constant for this particular reaction. There are collections of equilibria constant for particular reactions all over the place. And it's something that has to be measured experimentally. It's not something that you can deduce just by looking at the equation. Okay. Now we have the equilibrium constant for this reaction here. Now, what if we care more about the reaction of ammonia gas? Sorry, that's a 3. Decomposing to form nitrogen gas and hydrogen gas. Okay. What if we care more about this reaction? We want to know what happens here. What is the K for this reaction? Okay. Well, two things are happening here. Two things are happening in the original reaction, right? Number one, reaction is reversed. And number two, the reaction is multiplied by n equal 1/2. Right? We're taking half of the original equation. So the first step, number one, when the reaction is reversed, we take the inverse of K. Okay, so K reverse is equal to 1 over K forward is equal to 1 over 5.6 times 10 to the 5. Okay, and that is equal to 1.8 times 10 to the minus 6. Okay, and number two. The new K, we'll just call this K prime, I guess, is equal to K raised to the n value. Okay, so K prime is equal to 1.8 times 10 to the negative 6 raised to the 1/2 value. Okay. When you raise something to the 1/2, it's equal to the square root of that thing. So it ends up being k prime equal to 1.3 times 10 to the minus 3. Okay. This is the new equilibrium constant for this particular chemical reaction. Okay, so that's why it's so useful to know the connection between the equation and the rate constant, and the equilibrium constant itself, simply because you can look up the equilibrium constant for one reaction and figure out exactly what the equilibrium constant should be for a related reaction. Okay. So let's look at a particular class of reactions. Okay. Let's look at equilibrium. Let's look at gaseous reactions. Okay. In the case of a gaseous reaction, we don't typically talk about concentrations. Right? What we talk about more, and what we're going to use more if we have a gaseous reaction, is the partial pressure. You guys remember learning about this? I think it was, oh gosh, was that chapter 11 maybe? I think it was chapter 11. Okay, partial pressure is proportional to concentration. Okay, and since it's proportional to the concentration, for example, if we have some reaction here between SO3, or actually not between SO3, but SO3 is decomposing into SO2 and oxygen gas. Okay, so in this case, the equilibrium constant that we would form based on the concentration, I'm just going to call that Kc, would be equal to the products, SO2 squared times O2 divided by SO3 squared. Okay, so this is the Kc, or the equilibrium constant based on the concentration. Okay, we could form something called the Kp, which is the equilibrium constant formed from the pressure or the partial pressures, and you form it in exactly the same way. Instead of using the concentrations, you would use the partial pressure of SO2 raised to the value of 2 multiplied by the partial pressure of O2 divided by the partial pressure of SO3 raised to the second value, raised or squared. Okay, and importantly, these are all in ATM units. So always put in atmospheres. Okay. Oh, and in this case, always use molarity. Always use molarity. Okay. So the units are important for what you put in to each of these guys. The units are very important, but we don't necessarily ever talk about the actual units of Kp or Kc. Okay. We don't really write out the units of Kp and Kc, and we don't really talk about them that much. And this is just because they've been normalized. And I'll talk about that a little bit later in the chapter. But for now, what you should know is always use molarity for Kc, and always use atmospheres for Kp. Okay. Now, if the gases are ideal in our chemical reaction that's happening in the gaseous phase, okay, on page 685, there is a derivation using the ideal gas law. Okay, an ideal derivation using the ideal gas law, which relates the concentration of A to the number of A divided by the volume. Okay. I'm not going to get into this derivation at all, but if you're curious or you want to know more, check out page 680. Oh, that's an 8. 685. Okay. So if it's ideal, we can say that this is true. Okay. And because that, we can write Kp as being equal to Kc multiplied by RT to the delta N. Okay. For some reaction, A times A plus B times B goes to C times C plus D times D. Okay. That's the generalized reaction we're talking about here. And delta N, then, in this case, so this is the guy that gets RT gets raised to. Delta N is equal to C plus D minus A plus B. Okay, and this is just equal to the sum of products. Oops, maybe I should just write sum of N for the products minus the sum of N for the reactants, where N are just the stoichiometric values in front of the reaction itself. Okay. Okay, so delta N is equal to the change in the number of moles, and that is what is RT is raised to in this equation. Okay, so Kp does not necessarily equal Kc. Okay, we have some relationship between Kp and Kc and Kp here. Okay, but they don't necessarily equal to each other. And this is the relationship to figure out one based on the knowledge of the other. And of course, this is only if the gas is ideal. For the most cases, we assume that the gas is going to behave ideally. There are rare occasions when we can't, but we're really not going to run into many of those in general chemistry. So you can basically always assume that the gas is ideal unless I or the book tell you otherwise. Okay, let's run through an example of this. Okay, so say we have some reaction between NO gas and oxygen gas to form NO2 gas. Okay, we have a Kp for this. Say we measured it or we looked it up in a book of 2.2 times 10 to the 22 at 25 degrees C. Okay. How about Kc? What does Kc equal? We know Kp, therefore we can use this relationship up here to calculate Kc. Okay. So we have Kp is equal to Kc times RT to the delta N. We have to rearrange this a little bit to get Kc on one side. So Kc is equal to Kp multiplied by 1 over RT raised to the delta N. Okay. Now we have an expression for Kc explicitly, and we can calculate what it is. First, though, we need to know delta N. Delta N, again, is the sum of N for the products minus the sum of N for the reactants. In that case, this equals, let's go back up to our equation. So we have, for the reactants, we have 2 and 1, and for the products, we have 2. Okay, so that would be 2 for the products minus 2 plus 1 for the reactants. Okay, does that make sense? So our overall delta N is equal to negative 1. Okay, so then that means that we take Kc is equal to Kp, which is 2.2 times 10 to the 22. And we multiply it by 1 over, actually, 1 over the ideal gas constant multiplied by the temperature. So let's do 0.08206 liter atmospheres per mole Kelvin multiplied by the temperature, which is 25 degrees C. That was given to us up here, which is in Kelvin 298 Kelvin, raised to the delta N, which is -1. Kelvins cancel out, and we are left with, let's see, Kc is equal to 5.4 times 10 to the 13. And again, no units are used here. Okay, no units. It's just by convention that we don't write units with Kc, mostly because it gets really confusing really quickly. But just remember, okay, anytime you use this relationship between Kp and Kc, P always in atmospheres, volume always in liters, and N always in moles. Okay? And that means that you can only use the R value 0.08206 liter atmospheres per mole Kelvin. Okay, you can't use any others because you have to have these units for all of the unit shenanigans, which I'll get to later, to work out. Okay, so you have to use these units to make it work. Okay, and I think I will end it there for today. We've gotten through a significant amount of material. Let you guys digest that material down a little bit. Don't forget, the homework is due later this evening. If you have any questions, feel free to email me, chat me on Google Hangouts, ask about it in the Jamboard, or you can even go and get some tutoring. I posted a tutoring schedule for our tutors, Sean, Drake, and Sam. So if you need those, check it out on Canvas. I made an announcement. Yeah, and I hope you guys have a fantastic Monday. And I will see you, not really see you, I will virtually feel your presence back here again on Wednesday. All right, take care.